Alright guys, we're going to continue with the theme of logarithms and exponentials. So to make these concepts a little more clear, we're going to look at expressions in logarithmic form and we're going to translate them into exponential forms. So the way we're going to do it is, for example, here I have a logarithm base 27th. So I'm going to raise both sides to 27 to both sides of this expression. So I would have 27 to the power of logarithm base 27 of 3, and then 27 to the 1/3. And then exponentiation and logarithms are inverse functions of each other. So whenever you do 27 to the logarithm of base 27 of something, then you get that something back. So you have that 3 is equal to the cubic root of 27. So this would be the exponential expression because you're writing one side as an exponent or as a number to a certain power. So this would be your expression in exponential form. Similarly, if you do the same procedure here, you have base 5, so you would raise this and you would have that 25 is equal to 5 squared. So basically, if you read it in terms of the logarithm base 5 of 25 equals 2, what it's telling you is that you need to raise the base 5 to the power of 2 to obtain the argument of the logarithm of 25. So if you rewrite this expression in the following way by multiplying times -1 and you raise everything or b to the powers of both sides of the equation, what you're going to have is that v is going to be equal to b to the -w. So this would be the equivalent. These are two equivalent expressions, just one is given in logarithmic way, the other is given in exponential way. So in the exact same way we did before, but instead of exponentiating something, we can take logarithms and we can rewrite an exponential expression into logarithmic form by taking, for example, here the base would be 10, so you take log base 10 on both sides, and you obtain that since log base 10 and 10 to the power of 3, you have logarithm and exponential function. These are inverses of each other. So what you obtain is that 3 would be equal to the log base 10 of 1000. And similarly here, the base now is q, so you get that n is going to be log base q of t. So why do we look at this, or why do we care about this? Is because we're going to use this to solve equations. So before I had expressions that didn't necessarily involve a variable, but here we do. So for example, if I want to solve for the variable t in this expression, what I would have to do is take logarithm base e, or natural logarithm, on both sides, and I get the natural logarithm of e to the 3t is equal to the natural logarithm of 900. Now, natural logarithm and exponentiation are inverse to each other, so I just get the argument, or the exponent in this case, sorry. So I get that 3t is equal to the natural log of 900. And to solve for t, I can divide by 3. And I obtain that t is, if you want, 1/3 of natural log of 900. And if you like everything as a single logarithm, you could put this factor 1/3 as an exponent inside of the logarithm. So you'd get cubic root of 900. So you could do that if that is, if you prefer to write it that way. All right, and similarly here, you can since I have t in the exponent, I need to bring it down if you want, so that I can solve for t. So to bring it down, I'm doing quotations in the air, but you cannot see it. But to bring it down, you take logarithm on both sides, and in this case would be the natural logarithm because that's my base, e, and I obtain 0.07 t, and I'm skipping a step and I shouldn't do that. Let me go back. Let me take the natural logarithm, and I forgot my t equals to a natural logarithm of 2, and then this gives me just what I was going to write a second ago, just 0.07 t equals natural log of 2, and then I can divide both sides by 0.07. Natural log of 2, and this would give me an approximate value if I plug in the calculator. Let me do that, and I'll give you the answer. That is roughly 9.9. All right, so we're going to be using, we're going to be solving exponential and logarithmic equations in the next section. That's why I touched on this. But the main goal of this video, or for the rest of this section, is to calculate the derivative of the natural log. So if x is greater than 0, why do we have that? Well, that is just so that the natural log is well defined. Remember, the natural log, the domain is only the positive numbers. So the derivative of the natural log is 1 over x, the natural log of x, I should say. And if instead of x you have a function of x, in that case u, then the derivative of the natural log of u would be the derivative of u, or derivative of the inside if you want, over u, or over the inside. So let's solve a few examples. I have 3 right here for you. The first one is just simple. We have derivative of this. You copy the constant because you don't, this constant just goes along for the ride, and then you multiply times the derivative of the natural log. Derivative of the natural log of x is just 1 over x. So you could rewrite this as negative 9 over x. So that's the first one. Now let's make it a little more complicated by putting a product rule. So you have two factors, x to the 5th and natural log of 3x. So we need to do a product rule because you have a product. So derivative of g in this case would be derivative of the first. This one is just 5x to the 4th times the second. So just copy the second plus copy the first times the derivative of the second. Now, remember what I said about the derivative of natural log of u is u prime, which in this case is 3, over u, which in this case u is 3x. So when you simplify things here, you get 5x to the 4th, natural log of 3x, and here 1x cancels 1x, 3 cancels 3, so plus x to the 4th. And you can see how you can factor x to the 4th, and you get 5 natural log of 3x plus 1. You could still write this natural log of 3x to the power of 5, but let me leave it like that right now. Now, this one right here is a great example because it shows you that you sometimes can use the properties of logarithms to make your life a little simpler. So what do I mean by that? If I were to take my derivative directly here, I would have derivative of the inside. Well, the inside is a quotient, so I would need to do a quotient rule, and then divided by the inside. So I would have an expression with two different fractions divided by each other. Not very nice, but you can always use the rules of logarithms to write this. Since you have a division, you can write it as the difference of the logarithms. So in this case, it could be natural log of x plus 5 minus natural log of x. That is just using the rules of logarithms. So now I can take the derivative of this expression, which is a lot simpler because I just do derivative of the inside for this one. Derivative of the inside is just 2x over the inside, x squared plus 5, minus derivative of natural log, which is 1 over x. You could do a common denominator and whatnot, but that expression is perfectly fine. And you see how this was a lot faster. Let me do the common denominator just because whenever you solve the problems in your homework, you will be asked to simplify things. So how would you do that? Well, you put the product of the denominators as the new denominator, and then you just cross multiply here. You get 2x squared minus 2x squared, minus x squared plus 5. And that becomes just 2x squared minus x squared is going to be x squared, and then minus 5. All right, and that gives you a nice expression for your derivative. All right, I'll leave this video here. If you have any questions, ask me during the conference session, or you can put your comments in the comments below. Your questions in the comments below. Thank you for watching.